For generations, the daily chore of summer gardening has meant standing in the heat with a hose, trying to provide enough water to keep the backyard alive until the next sunrise. This method has a major physical flaw. When water hits hot topsoil, a massive percentage is lost to rapid evaporation before it ever travels deep enough to reach the roots. With over 38% of the U.S. currently facing drought conditions and municipal water restrictions, this wasted evaporation is a luxury that modern gardens cannot afford. We can build genuine water resilience by replacing surface-level sprays with a passive, three-dimensional management system. Shifting our approach from active labor to structural engineering allows the garden to sustain itself, regardless of the heat. This blueprint demonstrates the first layer of spatial organization, hydrozoning. It organizes a plot by grouping plants based on their specific thirst levels. Heavy drinking crops are placed near the primary water source. Drought-resistant varieties move to the furthest edges, surviving with minimal intervention. This deliberate clustering also makes it simple to route alternative water sources, like safe household gray water, directly to the zones that need it most. Reorganizing the garden this way eliminates collateral water waste and prevents plant stress before the first drop of water is even deployed. Moving down to the soil surface, the next layer of the system relies on the no-dig philosophy. Tilling violently shreds natural soil architecture, destroying beneficial microbes and releasing trapped carbon directly into our warming atmosphere. Churning the earth also exposes thousands of dormant weed seeds to the sunlight, creating a cycle of constant, exhausting maintenance. The no-dig alternative protects the soil by layering organic mulch on top, creating a dense, moisture-trapping barrier against the sun. Leaving the ground undisturbed allows delicate mycorrhizal fungal networks to spread, acting like microscopic extensions of plant roots to find moisture. Treating the surface as an undisturbed armor outsources the labor of weeding and aeration to natural biology. The final layer of the system sits entirely underground, utilizing sub-irrigation to bypass the atmosphere. A modern wicking bed uses a built-in water reservoir at the very bottom, physically separated from the soil layer above. This system delivers moisture directly to the root zone by wicking water upward through the soil, moving against gravity. For an even simpler approach, gardeners use the ancient olla pot, an unglazed clay vessel buried neck-deep in the soil. Both systems are powered by a physical phenomenon called soil moisture tension. Dry soil acts as a physical vacuum, pulling water molecules out through the porous clay until the area reaches equilibrium. This process is self-regulating. The flow halts the moment the surrounding soil reaches optimal moisture. Moving the delivery underground makes surface evaporation impossible, saving up to 70% of the water used in traditional gardening. When combined, these three layers, hydrozoning, mulching, and sub-irrigation, form a unified, drought-proof system. This high-efficiency layout carries on a legacy of agricultural engineering built for survival in the world's driest climates. We see these principles in the deep, geometric architecture of ancient Indian stepwells, built to manage and protect groundwater from the sun. It appears again in ancient Persian qanats, which transported water through miles of underground tunnels to prevent evaporation losses. A drought-proof garden succeeds by working with these ancient laws of physics and letting the earth water itself.